I'm finding it hard to write a blog this week because I spent most of my week in my room doing this. This took me an hour. It's a standard day. So I thought I'd make a little video instead. This is something I learned in nuclear and particle physics, and it is the only evidence so far for physics beyond the Standard Model. And it's talking about neutrinos. In the Standard Model, neutrinos are these like little massless particles that just go along at the speed of light, don't really do much, don't really interact with anything. They're produced in the sun, and because they don't really interact with anything, they shine down on you in the day, and then they shine up through the Earth on you in the night, which is pretty cool. So you always have billions of neutrinos streaming through you. So there are three types of neutrinos. And we know that when solar rays hit the upper atmosphere, these first two types are produced in a ratio of 2 to 1. And if they were just normal neutrinos, massless, chilling along as they should be, that would be the ratio you'd see wherever you measured them from. So scientists, this is the Earth. They put a detector here, a bit underground to shield it from background radiation, and they measured the neutrinos that they saw when the sun was above, the two types of neutrinos, shining down here and producing neutrinos in the atmosphere here. And they saw this ratio, the 2 to 1 ratio. And they were like, yeah, that's good, it matches our predictions. And then they also did the measurement when the sun was below. And the neutrinos were shining down here and producing the atmosphere. But this time they travelled like an extra 12,000 kilometres through the Earth, which is, as we've mentioned, is no problem for the neutrinos. But this time they saw a 1 to 1 ratio, which is really odd because it doesn't match the prediction and what's going on here. Which suggests that neutrinos had flipped type while they were travelling, which is big news because that means that they must have a really, really small mass, like too small to see experimentally, maybe like 0.05 an electron volt, which is really, really small. But yeah, and that is quite rogue because it means it breaks conservation laws because the different types are in different like families that are normally always conserved in reactions, and this time they're not, so that's really strange. It must be a really small, weak effect. But yeah, it's pretty interesting. That's fact number 1. The second thing is about why you never see particles that have colour charge existing on their own, and why you only have things like protons and neutrons are all bound together. Colour charge is like electric charge, but for the strong force, whereas electric charge is obviously for the electromagnetic force. And in the Standard Model of particle physics, then each force has its own charge carriers. And the electromagnetic force, the charge carriers are photons, which we see as light, and the strong force carriers are called gluons, and there's actually 8 types of them, but they're basically the same as photons. Like, they're pretty chill. They both have no mass, so they have infinite range, which means they should behave like almost the same, which is odd because we have photon lights, we have lights, but we don't have gluon lights or gluon power stations or anything like that. You never see these particles going around, and that is because gluons themselves carry colour charge, which is really odd. Photons don't carry any charge, so they can't interact with other photons. But gluons can carry colour charge, and that's why there's 8 types of them, because there's like lots of different kinds of colour charge. But this basically means that they can self-interact, and they can also branch off. You might have seen a picture like this with an electron or something with electric charge, radiating these little field lines out into space just for infinity. And that's fine with the electric charge, because the field lines obviously get less dense as you go further out. So the force gets weaker the further away you go, which enables them to be fine in the universe. But if you had something with colour charge, like a quark, its field lines, because gluons can radiate other gluons, would just continue to multiply and multiply and multiply. So the further away you went, like there's no change in the strength of the force. And if there's no change in the strength of the force over the whole universe, that requires like infinite energy. It can't be done. So this means that they must always be bound together in colour neutral things like protons and neutrons, and like it's why 3 quarks or 2 quark pairs only exist in nature. And this is why it's really hard to measure the value of the strong force, because like how do you measure a force if all the particles you see are charged neutral overall? I hope you liked my video.